Hi, I want to talk about another problem from Kleppner and Kolenkow. This is problem 1.4, where we're talking about vectors and vector operations, and in this problem we're discussing direction cosines. So for a given vector, these are the cosines of the angles that our vector makes with the three coordinate axes, alpha, beta, and gamma. So let me draw that a little more carefully. So if this is our vector r, here's our vector, and our coordinate axes, which I'll draw in gray, look like this. So here's z-axis, z hat, and then that means we have x hat coming out like this, x hat, and then here's y hat. So if these are our three vectors, then our direction cosines are defined in terms of these three angles. So here's gamma, the angle that r makes with the z-axis, and then here's beta, the angle it makes with the y-axis, and a little harder to draw, but here's alpha, the angle that r makes with the x-hat axis. So we want to show this particular identity about these three angles, alpha, beta, and gamma, using either geometry or vector algebra. I prefer to do this with vector algebra, and let me show you a neat way to do this. So first let me write the vector r. So the vector r in components, it has components along x, y, and z, and I can do that in this neat way. So this is r dotted with x hat in the x hat direction, plus r dotted with y hat in the y hat direction, plus r dotted with z hat in the z hat direction. So this is just the standard decomposition of a vector into its components along the three coordinate axes. Remember, the dot product gives you this component because the dot product of r with x is the magnitude of r times the magnitude of x times the cosine of the angle between them. But the magnitude of x hat is 1 since it's a unit vector, and the magnitude of r we can just write with this magnitude of r symbol. So magnitude of r, so I'm pulling out this magnitude of r from each of the three terms. So then using this definition of the dot product, where the dot product of a and b is magnitude a, magnitude b, cosine of the angle between them. Well, the cosine of r with x hat is alpha by definition. So here's a cosine alpha x hat. And now you see what's happening. So each of these gets the cosine of the corresponding angle. So we get a cosine beta y hat plus a cosine of gamma z hat. So that's pretty good. Now we want to show that the sum of the squares of these cosines is 1, but this is pretty easy because we can define a unit vector now. So if we divide both sides by the length, which is norm r, then that means r hat, which is r over the size of r, the magnitude of r, is the sum of these three, cosine alpha x hat plus cosine beta y hat plus cosine gamma z hat. But this is a unit vector. So unit vector means that r hat dotted with itself equals 1, but then the dot product of this right-hand side with itself is just this thing times itself plus this thing times itself plus this thing times itself. So I'm just taking the dot product of this by multiplying each of the three components by itself. So that gives us cosine squared alpha plus cosine squared beta plus cosine squared gamma. So that was what we needed to show, that the sum of those three gives 1. So to recap, all that we needed to do was use the decomposition of a vector into its components along the three coordinate axes, and then use the definition of the dot product involving the two norms and a cosine, and then make this unit vector and take its dot product with itself. So we've solved the problem. Thanks for watching.